Welcome everybody. Thank you for joining my presentation about how Milan unlocks AVB TSN for especially audio applications. I've been involved in the specification work of Milan from the very first hour. Back then I was working with D&B Audio Technique, so we started that initiative in 2016. And what I found then is that it's still very complicated to implement this stuff. Although everything is specified and standardized, it's still a challenge for manufacturers to get this stuff implemented. And with that idea in mind, I founded JOYNED. So JOYNED is a provider of software solutions for manufacturers of audio equipment. But today we will talk more about what is actually Milan, how does it make things better for you in audio applications. First of all, what is AVB and what is Milan? So there is a set of specifications for what we call end stations. This is microphones, mixers, can be loudspeakers or other equipment in the signal chain. And Milan builds up on the AVB specification, which is basically an IEEE standard, which is still relevant for switches. So we need switches that support AVB. What that means in detail is something we will discover in the following presentation, but in principle, this is all you need to know to run an AVB Milan network. You need AVB switches, you want equipment that is Milan certified, and that allows you to bring audio from A to B, because that's what it's all about at the end of the day. We want to get audio from A to B in good quality, and we want to use the network for that. Who supports Milan? There is a big collection of manufacturers, very renowned brands, and also new brands who collaborate. Even strong competitors come together, collaborate on specifying Milan. Now, the third element, we talked about switches, we talked about end stations, we also need a controller to operate the network. So the third element you need to run a network is some sort of controller. And there is a variety of solutions available. There's Hive, which we consider more as a development tool. It's an open source project. So if you want to get a bit more into details, that's an interesting solution to look at. Then there's the Milan Manager. That's a solution that is neutrally branded, but was developed in a collaboration from L Acoustics and D&B. So that can be seen as the universal neutral tool that everyone can use, independent of the manufacturer, to operate a Milan network. And then a bit of different approach, a more visual approach to make connections is Nebra from Myosound. It is a solution solely developed by Myosound, but also works for every standardized Milan product. So we did a lot of market research and talked to users and tried to figure out what is the real pain point. And what we hear is, I don't want to be an IoT expert. It is still complicated to to configure switches with the existing solutions. Then important requirement is, once it's set up, I want it to be stable. I don't want to bother with, is there any dropouts, is there synchronization issues, stuff like that. And some even go as far saying it should be as simple as analog connections. The good old XLR is still what I want to have, but I also want the flexibility of a network. So it boils down to, we have an issue with switch configuration and management. We need a very reliable solution, and we clearly see a trend for open standards because there's an interoperability needed. We never see systems where everything comes from one brand. Usually there's a mixing desk from one brand, there's the microphone from another, and the loudspeaker is also from another. So we need these standardized interfaces between them. So in 2016, D&B, L Acoustics, Myosound, IAM, Avid was a small group of manufacturers back then, came together and we agreed on a couple of principles. So we say we want this enhanced IEEE standards. What exactly that means is something we will dive a bit deeper into. But back then AVB was known to be not really interoperable. You could follow the standard, a manufacturer could implement it, but it did not necessarily mean that you can connect to an AVB implementation from another manufacturer. So we need true interoperability, and that means we need a scheme for media clocking, we need common stream formats, We need all this definition to interface with control solutions, with the control software. And we also found there is a lot of ambiguities in this IEEE standards. And we wanted to add a redundancy scheme. So if something in the infrastructure fails, the other part of the infrastructure can still deliver audio without any interruption. So that was the baseline for all this Milan specification work. Now, you might have noticed already that there's a couple of consortia and many different names and buzzwords around, so I would also like to take the opportunity to clarify that a little bit. IEEE is the consortia that defines many basic things like Wi-Fi. The underlying technology is defined in IEEE standards. All our internet, all network we do, Ethernet, is defined in IEEE standards. So this is a very important consortia for a lot of technology that is commonly used. Then we have the Avenue Alliance. The Avenue Alliance is basically the body where these manufacturers come together, and it gives a legal framework to do this work. And from the Avenue Alliance, the Milan specification gets defined, and Milan is basically a trademark to give the whole thing a name. We didn't want just to have an IEEE standard with just another number. We wanted to be able to give it a name, and that's Milan. But it builds up on IEEE standards. Avenue is the consortia. So we end up working with IEEE standards and those Milan specifications, just to give that a bit context. So how does Milan compare to other existing solutions? I think what's important to understand is that everything builds up on IEEE standards. So it's not a black or white thing in that sense, but it's interesting to note that we keep developing these IEEE standards further. So Ethernet is a technology that was invented a bit more than 50 years ago, and it's still a relevant technology. So that's a very robust thing. But back then, it was not meant to be real-time. It was not meant to provide any means to do time synchronization. So it was just about data transfers. And nowadays, it's not only audio where this is relevant, it's also in automotive, it is also in industrial automation that we have these requirements, that we have high data rates, that we need to deliver reliably, and we need to add means for time synchronization. And that is what started with AVB. TSN is another buzzword in that context. It's basically just a renaming of this work group in the IEEE standards. And that adds all these deterministic synchronous features to Ethernet. And solutions like Dante, Ravenna, AES67QLAN, that's basically building up on legacy, what we call legacy Ethernet. So it's an older version of these IEEE standards, and that does not yet, maybe it will also in the future, but it does not yet leverage these new features of Ethernet to be deterministic. And that's what Milan fully leverages. Also interesting to know, as well as for manufacturers, but also for you as a user, is that there is a certification scheme. So if you see the Milan brand on a device, you can rely on the fact that the Avenue Consortium granted a certification for that, and that the device underwent some testing. So there is a well-defined set of tests that looks a bit complicated in that diagram. We don't need to go into details, but this is something we also help with as JOYNED to our customers to provide this as a service. The process for that is either the manufacturer or we as JOYNED generate test reports. It's an automated test that runs through. Then we have to go to an official test house that validates with a so-called quick test, and then the Avenue Alliance can grant this certificate. So if you see this Milan certification trademark on a device, you have full reliability that it fulfills everything that is specified. So we will go a bit more into details now. First, we talk about synchronization. So what makes the difference here? In a regular network, these devices do not have any time information. So if you look, for instance, at Dante, they use PTP-v1, which means there's a protocol where end station, like a microphone, and the loudspeaker directly communicate with each other and exchange time information, so we get synchronized audio at the end. What is not involved there is the switches. So we have an uncertainty in how long the packets take to get from one endpoint to the other. The fundamental change with gPTP, but also with PTP-v2, is that these switches become time aware. So they also play an essential role in all these time measurements and in the synchronization. We could do a whole presentation about PTP itself. We skipped that for today, but I think that's the most fundamental thing to understand, that every component in this network plays an important role in time synchronization. At the end of this presentation, we will wrap it up with a question: can Milan really sound better than other digital systems or other network standards? So keep that in mind, we will come back to it. Another important factor is latencies. Yeah, we want to keep latencies very short. And now, as we understand, we have a common time base in the network, we can also think a bit about what does it take to get audio samples from one end of a network to the other end. And the basic principle is we sample audio here, we have our AD conversion, we sample audio here, we take a timestamp that references to our common PTP time. These audio samples and the timestamp travel along on the network, and then we have received that in the loudspeaker in this example, and the loudspeaker has to wait until the so-called presentation time is reached. And that allows that if there is multiple loudspeakers, all loudspeakers can play out audio at exactly the same time. So we're really talking microsecond precision here, so really with subsample accuracy. And yeah, this is the basic concept how the timestamping is done. Now, what we want to guarantee is that no matter what load we have on the network, our packets do not get delayed. So we want to guarantee that these packets arrive in time. We cannot afford to lose any single frame. So giving here an example of loading the network with 360 channels, pushing that through two switches here. So that would equal to having 35% of the bandwidth reserved. Would still allow us to keep the latency as low as 0.4 milliseconds. With a fully loaded network with 360 channels, two switches in between, 0.4 milliseconds. Let's go a bit bigger. I would say this is already a very large network. In a large installation on a regular festival scenario, you will probably not find that many switches between your endpoints. But even if we have 9 hops, we can still achieve 1.2 milliseconds latency. So that's really impressive. And that's something that is not possible if you do not have means to really reserve this bandwidth and guarantee that we have this maximum of 137 microseconds as a rule of thumb. That's what you can use to calculate if you know how many switches you have. For each connection, for each hop, you add up this latency. That's what you have guaranteed in a Milan network. This is also summarized in this table. I'm happy to share the presentation with you just to have a couple of benchmarks. Also important to note here is there's often that rumor about AVB reserves this 75% and steals that away from other applications on the network. We will come back to that. But also the given latency figures, often this 2 milliseconds is a known number, but that applies only for the scenario with 7 hops, 100 Mbit link speed on all hops, then you can still achieve these 2 milliseconds. If we go up to gigabit or even further, we can do the same amount of hops with lower latency, or even on a 100 Mbit link, if we have less hops, we can reduce the latency. So this 2 millisecond thing is not a fixed thing. That's an old misperception of legacy AVB standards, basically. This is fixed for Milan. Then what does it mean to have stream reservation? So, and here I really try to start at the very beginning. I do not want to bother you with OSI layers. You have heard that often enough, I guess. And I think it causes more confusion than bringing clarity. But I think it's interesting to have a quick recap about what is an Ethernet packet. So in every packet that we send on a network, no matter if it's Dante, AVB, or whatsoever, we always have a destination MAC address. So we have an address identifier at the very beginning of the packet, which says where this packet is sent. Then we have a source MAC address. That's the second part here. So this is an identifier that is unique for the sending device. And then it goes further. We have a VLAN ID. So we have a identifier whether it's a VLAN or not. So also interesting to know that every AVB stream gets assigned to a VLAN. So we have a VLAN identifier. And then we have the ether type. So until here, there's nothing special about AVB. This is common for any IP packet, for anything that you will see on a network. The ether type defines whether this is an IP packet, or in case of AVB and Milan, we have a special identifier for making this an AVB packet. So our network infrastructure, our switches, can differentiate whether this is high priority AVB or if it is IP or any other thing. And then after that, AVB-specific things will follow, which we do not need to go into, but this is basically where you would find the timestamps and the audio samples. This is how every Ethernet packet is structured. And this is also what gives us the advantage that if we have unique MAC addresses here that can clearly identify a stream, the switch can go in very early and identify this is AVB, I need to handle that in a special way. What is a stream? A stream is basically a sequence of many of those packets. We send per stream, we send 8,000 packets per second. Each packet contains 6 samples per audio channel. So this ends up with having a really high packet rate, and we can have 150 of those streams. So just to have that clear, a stream is just a continuous transmission of these Ethernet packets. So now, what is special about AVB? First thing, we have the so-called multicast address allocation protocol. So every device here requests a unique multicast MAC address. That's the very first thing we want to put into our Ethernet packet. If every stream gets its unique multicast MAC address, then we have a pretty simple scheme in the switch to say, okay, I need just to look at this destination MAC address, and based on other information, I can then decide where to send it. But this is always a unique thing for every stream. So that's the first fundamental step to take here. Every stream has its own multicast MAC address. Then the stream reservation protocol, and I'm really trying to keep it simple. Practically, it's of course much more complex, but the basic scheme is something like the talker goes in. Here, in this example, we send a stream out from the mixing desk. So the mixing desk would register its stream on the switch. So all switches in the network know what streams are around on the network. Then a loudspeaker, for instance, can go in and say, I want to receive that stream from the mixing desk. And only if there is enough bandwidth, this mixing desk will start streaming. It will not send anything to the network if the switch and the whole infrastructure cannot guarantee that this bandwidth can be handled. And then it can also make easy decisions to say, okay, this is a loudspeaker that requested that stream, so I forward it. If it's not requested, it will not be forwarded. So we do not flood the network with multicast. We have a very clear rule where we send packets, only to those who request it. That's streamer reservation presented in a simple scheme. Now, this is a more complicated topic about queuing and shaping, so I will keep this very short today. But in principle, the thing I want you to understand is that we have special mechanisms now in the switch that allows us, because we have this multicast MAC address range, special for AVB, we can identify what packet it is. So we say, okay, this is an AVB packet. It is a MAC address that got a reservation, so I allow it to get in. If it's not reserved, I would not even allow it to get into the switch. Then I can have different queues, so it's like having one lane where I put all the high priority traffic in, which is our AVB traffic. And there might be some other control stuff coming from a laptop, some maybe OCA remote control stuff. That is not as time critical as delivering the audio. So we put that into the low priority queue. And then there is these so-called shapers that regularly inspect these queues and send out traffic in a very regular intervals. Now, I mentioned already that it's often heard that AVB steals away bandwidth from other applications. So the way this works is that only the bandwidth that is used for the streams that get connected and reserved is used. So let's say you have 48 channels on a link and you make reservations for that, then only these 10% are reserved for that stream. The other 90% of your gigabit link, which would be 900 Mbit, being just available for control and other stuff, still is available. So it's still a decision of the user how many streams you connect and how much bandwidth you have here. Now, another way to look at this is this 75% thing. You can see this more as a limit. If you have connected already 360 channels and you use this 75% for AVB, and now you would try to add another stream, the switches would say no. They are not allowed to reserve more bandwidth than these 75%. So this also implies that these remaining 25% are still guaranteed to be available for control. So it's not only about the guarantee for your audio data, it's also about a guarantee for all the other applications. And if you really need to, you can also adjust these thresholds. That depends a bit on the API of the switches, but in theory, depending on the vendor, you could adjust this value. That's possible. Yeah? Maybe also as a little tool when you plan a network, here's an overview how much bandwidth is really consumed, depending on the sample rate you use. Typically it's 48 kilohertz or 96 kilohertz. Then you can put a different amount of channels into a stream. Yeah? A microphone would typically be a single channel stream. If you have something like a stage box, it's more likely that you have streams where you have 8 packets of 8 channels and then multiple streams of those. In an 8 channel, just as a rule of thumb, maybe a number to remember is that you are around this 16.5 Mbit per second for an 8 channel stream at 48 kilohertz. So that's useful to have available as a rule of thumb, and it approximately doubles, little bit less, but that's how you can also plan your network and the required bandwidth. So now we come to the most exciting question. Can Milan really sound better? What do you think? Have you heard rumors about Milan sounding better? Yeah? Heard that?
Yes.
Is it true? What do you think? So let's dive into it. We start with the very basics. It starts with analog-digital conversion. So we need to understand that when we have an analog continuous signal, we look at this in certain time intervals. Then we get a quantized signal. And then when we want to convert that back to analog, we need to be exactly at the same time intervals to recreate this sampled value. If the timing here is slightly different, we will have an error in the reconstructed signal. That's just the basic for any AD-DA conversion. Now, what is jitter? So in simple terms, when we do a AD conversion, we need a clock. So we have a clock signal that defines these time intervals where we sample. So on these edges, we take an audio sample. So now when we go through a digital system, doesn't matter if this is Dante, MADI, or AVB, we have a digital system. So we need to transmit that clock to the other end. On that way, we will get some error in that clock, and that's the jitter. And depending on how much jitter we have, that will influence the quality of our DA conversion. So how bad can that get? Here's an example where we did a measurement where we introduced artificial jitter of 25 nanoseconds, and we see that the noise floor increases from minus 130 dB to something around minus 80. So if we had this jitter of 25 nanoseconds, this would be the resultant noise. So we can show that jitter has a significant impact. Now the question is, how much jitter do we really have? You remember we say we do gPTP because it is the PTP protocol that gives us the best synchronization. Yeah? So that's why we want to have every endpoint and every switch being involved in the synchronization. And this is really as good as getting an accuracy of plus minus 40 nanoseconds. So if we just generate a signal based on that clock, we get plus minus 40 nanoseconds error. That's not good enough yet, right? So in addition to that, we will also have PLLs that damp the jitter even further. But it is important to note that every element in this signal chain plays a crucial role in getting the timing as good as possible. Now, there was an AES paper published. My colleague Morten Laaf was involved in that, one of the renowned experts for timing things and network stuff. And we did an analysis about what is the worst case that can happen comparing PTP version 1, PTP version 2, and gPTP. And of course, it now can get very complicated depending on the number of hops, but let's take an example of 6 hops. You can see that in the gPTP network, we get an error of 0.063 microseconds. Then if we look at PTPB1, that's the worst case where we get 2,500 microseconds error in the reconstructed clock. So what does that mean for our audio signal? If we take an example where we look at a line array with 12 elements and we analyze the frequency response in some reference point here, then we can calculate how much error we get in the frequency response depending on the timing error. And this is the result. If we have a perfect clock, we have a very minimal error in the frequency response. So that's what we can achieve with gPTP. So here we take the error of PTP into account, and we get a very small variation here in high frequencies. If we take the worst case scenario for PTPv1, which can practically happen when you have a heavily loaded network, you can get something beyond plus minus 6 dB error at 20 kilohertz, and it starts already rolling out here at 1 kilohertz above. You get a significant error in the response. So I'm not saying here that this is always happening. Yeah? So when you have a stable network, you might be okay, but when a situation occurs where you load the network and you have a spontaneous thing going on with a lot of remote control data, this can happen. So that's it from me. If you want to start your product development with JOYNED, we have solutions for XMOV microcontrollers. We're working on switches with Marvell. We have analog devices, so the logo got blurred here. So we have solutions for several platforms, easy to start with. Hope you learned something, and yeah, don't hesitate to reach out if you have questions. And yeah, thank you for listening. I'm still available for questions, I guess we have.